In Euclidean geometry, a convex quadrilateral with at least one pair of parallel sides is referred to as a trapezoid in American and Canadian English, but as a trapezium in English outside North America. The parallel sides are called the bases of the trapezoid and the other two sides are called the legs or the lateral sides. A scalene trapezoid is a trapezoid with no sides of equal measure, in contrast to the special cases below. Etymology. The term trapezium has been in use in English since 1570, from late Latin trapezium, from Greek tau rho alpha pi epsilon zeta iota omicron nu, literally, a little table, a diminutive of tau rho alpha pi epsilon zeta alpha, a table, itself from tau epsilon tau rho alpha sigma, 4, plus pi epsilon zeta alpha, a foot, an edge. The first recorded use of the Greek word translated trapezoid was by Marinus Proclus in his commentary on the first book of Euclid's Elements. This article uses the term trapezoid in the sense that is current in the United States and Canada. In many other languages using a word derived from the Greek for this figure, the form closest to trapezium is used. Special cases. A right trapezoid has two adjacent right angles. Right trapezoids are used in the trapezoidal rule for estimating areas under a curve. An acute trapezoid has two adjacent acute angles on its longer base edge, while an obtuse trapezoid has one acute and one obtuse angle on each base. An acute trapezoid is also an isosceles trapezoid, if its sides have the same length, and the base angles have the same measure. It has reflection symmetry. An obtuse trapezoid with two pairs of parallel sides is a parallelogram. A parallelogram has central twofold rotational symmetry. There is some disagreement whether parallelograms, which have two pairs of parallel sides, should be regarded as trapezoids. Some define a trapezoid as a quadrilateral having only one pair of parallel sides, thereby excluding parallelograms. Others define a trapezoid as a quadrilateral with at least one pair of parallel sides, making the parallelogram a special type of trapezoid. The latter definition is consistent with its uses in higher mathematics such as calculus. The former definition would make such concepts as the trapezoidal approximation to a definite integral ill-defined. This article uses the inclusive definition and considers parallelograms as special cases of a trapezoid. This is also advocated in the taxonomy of quadrilaterals. Under the inclusive definition, all parallelograms are trapezoids. Rectangles have mirror symmetry on mid-edges, rhombuses have mirror symmetry on vertices, while squares have mirror symmetry on both mid-edges and vertices. A Sarkari quadrilateral is similar to a trapezoid in the hyperbolic plane, with two adjacent right angles, while it is a rectangle in the Euclidean plane. A Lambert quadrilateral in the hyperbolic plane has three right angles. A tangential trapezoid is a trapezoid that has an incircle. Characterizations. Given a convex quadrilateral, the following properties are equivalent, and each implies that the quadrilateral is a trapezoid. It has two adjacent angles that are supplementary, that is, they add up to 180 degrees. The angle between a side and a diagonal is equal to the angle between the opposite side and the same diagonal. The diagonals cut each other in mutually the same ratio. The diagonals cut the quadrilateral into four triangles of which one opposite pair are similar. The diagonals cut the quadrilateral into four triangles of which one opposite pair have equal areas. The product of the areas of the two triangles formed by one diagonal equals the product of the areas of the two triangles formed by the other diagonal. The areas S and T of some two opposite triangles of the four triangles formed by the diagonals satisfy the equation, where K is the area of the quadrilateral. The midpoints of two opposite sides and the intersection of the diagonals are collinear. The cosines of two adjacent angles sum to zero, as do the cosines of the other two angles. The cotangents of two adjacent angles sum to zero, as do the cotangents of the other two adjacent angles. 1b median divides quadrilateral into two quadrilaterals of equal areas. twice the length of the B-median connecting the midpoints of two opposite sides equals the sum of the lengths of the other sides. Additionally, the following properties are equivalent, and each implies that opposite sides A and B are parallel. The consecutive sides A, C, B, D and the diagonals P, Q satisfy the equation. The distance V between the midpoints of the diagonals satisfies the equation. Midsegment and height. The midsegment of a trapezoid is the segment that joins the midpoints of the legs. It is parallel to the bases. Its length m is equal to the average of the lengths of the bases A and B of the trapezoid. The midsegment of a trapezoid is one of the two B-medians. The height is the perpendicular distance between the bases. In the case that the two bases have different lengths, the height of a trapezoid H can be determined by the length of its four sides using the formula where C and D are the lengths of the legs. This formula also gives a way of determining when a trapezoid of consecutive sides A, C, B, and D exists. There is such a trapezoid with bases A and B if and only if area. The area K of a trapezoid is given by where A and B are the lengths of the parallel sides, H is the height, and M is the arithmetic mean of the lengths of the two parallel sides. In 499 AD, Aryabhata, a great mathematician-astronomer from the classical age of Indian mathematics and Indian astronomy, used this method in the Aryabhatiya. This yields as a special case the well-known formula for the area of a triangle. By considering a triangle as a degenerate trapezoid in which one of the parallel sides has shrunk to a point, Milloy's rule takes this a step further by considering the circumference of a circle and its center point as the parallel sides and the radius is the perpendicular distance between them to give the area of the circle. From the formula for the height, it can be concluded that the area can be expressed in terms of the four sides as when one of the parallel sides has shrunk to a point. This formula reduces to Heron's formula for the area of a triangle. Another equivalent formula for the area, which more closely resembles Heron's formula, is where is the semi-perimeter of the trapezoid. The formula is also a special case of Brett-Schneider's formula for a general quadrilateral. From Brett-Schneider's formula, it follows that the line that joins the midpoints of the parallel sides bisects the area. Diagonals. The lengths of the diagonals are where A and B are the bases, C and D are the other two sides, and are less than B. If the trapezoid is divided into four triangles by its diagonals AC and BD, intersecting at O, then the area of AOD is equal to that of BOC, and the product of the areas of AOD and BOC is equal to that of AOB and COD. The ratio of the areas of each pair of adjacent triangles is the same as that between the lengths of the parallel sides. Let the trapezoid have vertices A, B, C, and D in sequence and have parallel sides AB and DC. Let E be the intersection of the diagonals, and let F be on side R and G be on side BC such that FEG is parallel to AB and CD. Then FG is the harmonic mean of AB and DC. The line that goes through both the intersection point of the extended non-parallel sides and the intersection point of the diagonals bisects each base. Other properties. The center of area lies along the line joining the midpoints of the parallel sides, at a perpendicular distance x from the longer side B given by if the angle bisectors to angles A and B intersect at P, and the angle bisectors to angles C and D intersect at Q. Then more on terminology. The term trapezium is sometimes defined in the US as a quadrilateral with no parallel sides, though this shape is more usually called an irregular quadrilateral. The term trapezoid was once defined as a quadrilateral without any parallel sides in Britain and elsewhere, but this does not reflect current usage. According to the Oxford English Dictionary, the sense of a figure with no sides parallel is the meaning for which Proclus introduced the term trapezoid. This is retained in the French trapezoide, German trapezoid, and in other languages. A trapezium in Proclus' sense is a quadrilateral having one pair of its opposite sides parallel. This was the specific sense in England in 17th and 18th centuries, and again the prevalent one in recent use. A trapezium as any quadrilateral more general than a parallelogram is the sense of the term in Euclid. The sense of a trapezium as an irregular quadrilateral having no sides parallel was sometimes used in England from c. 1800 to c. 1875, but is now obsolete. This sense is the one that is sometimes quoted in the US, but in practice quadrilateral is used rather than trapezium. Application in geometry. The cross-ladders problem is the problem of finding the distance between the parallel sides of a right trapezoid, given the diagonal lengths and the distance from the perpendicular leg to the diagonal intersection. Architecture. In architecture, the word is used to refer to symmetrical doors, windows, and buildings built wider at the base, tapering towards the top. In Egyptian style, if these have straight sides and sharp angular corners, their shapes are usually isosceles trapezoids. This was the standard style for the doors and windows of the Incas. Application in biology. In morphology, taxonomy and other descriptive disciplines in which a term for such shapes is necessary, terms such as trapezoidal or trapeziform commonly are useful in descriptions of particular organs or forms.